In the last lecture, we have seen the discontinuous mode of operation of the buck converter. So we have arrived at the voltage gain, that is M of D, for discontinuous conduction of mode, and whatever is the expression of M of D which we have derived in the previous lecture, it can further be simplified because we have to replace the expression, because in the expression of M of D we have to replace delta IL in terms of the known parameters. So this equation number 3 was the relation of V0 versus Vin. V0 by Vin is R into under root of D into 1 minus D delta L by 4 into LD F switching Vin. The thing is, LD means inductance, which is a given quantity, but we have to replace this delta L. So for replacing it in terms of delta L, we'll use this equation. VL is L delta L by dt. Now here delta L is not the delta L in discontinuous conduction mode, it is for the continuous conduction mode. So we can replace delta L as from this expression V into D by F switching L. So substituting delta L, which is in equation number 4, into equation number 3 and solving it, what we can get is the expression of V0 versus Vin, which is the equation number 5. Let me write it, equation number 5. So V0 by Vin, that is M of D for discontinuous mode, is D into R by 2L F switching into under root of 1 minus D. So let's assume that the term R by 2L F switching is K. So M of D for discontinuous conduction mode, which is this, is K D into under root of 1 minus D. This is for discontinuous conduction mode, and for continuous conduction mode, M of D for C means continuous conduction mode, is only D, because V0 by Vin is D. Now if you want to compare and plot M of D for continuous versus discontinuous conduction mode, we have to do a few assumptions. The assumptions are that the switching frequencies for both the cases, the converter is same, which is a buck converter. The only thing is that the converter operates in different modes, and the reason for discontinuity in the buck converter can be two reasons. First thing is insufficient inductance, that is inductance less than L critical. Second thing is no load or very less load. But rest of the things should be similar if we want to compare the M of D for continuous versus M of D for discontinuous conduction mode. So switching frequency, Vin, I load means the loading condition. So these terms should be same. That is, we'll assume that if I load is same, which means that we'll assume that R is same. So in this case, the reason of discontinuity is only one, that is insufficient inductance. So the only thing that varies in the discontinuous versus conduction continuous mode is the inductance. So that's why here I have written in equation number, let me write the equation number as 6. In equation number 6, L for CCM is not equals to L for DCM, or you can write L for discontinuous conduction mode is less than L for continuous conduction mode. D or DCM, both you can write. L of T less than L CCM. So rest everything is same. So now let's plot M of D for D versus M of D for C versus D. So here we'll write everything in terms of K. So K is R by 2L F switching. This is the value of K. So this is how the plot looks like. It looks very similar to a second order polynomial, falling polynomial. Now with this expression for M of D for discontinuous conduction mode, so you can see there are some peaks, that is these points where D is equals to D max. That is only for discontinuous conduction mode. What is the duty cycle at which you will get the maximum gain? So for finding only in discontinuous conduction mode, what is the maximum gain? That is D equals to D max. What we'll do is we'll differentiate the expression of M of D with respect to D. So we'll write dou M by dou D, which is equals to this, and if you solve it, you will get D max as 2 by 3, that is 0.67. So if a converter operates if a buck converter operates in a discontinuous conduction mode, then at this duty, that is 0.667, you will get maximum gain out of it, irrespective of the loading condition and other voltages. You just have to make sure that the converter is in DCM. So you'll get at this duty, you'll get the maximum gain for any power rating of buck converter. Now we can also find the point of intersection of this continuous conduction mode versus discontinuous conduction mode voltage gains, that is m of d of c being equal to m of d of d. So what we'll do is we'll just equate it. What is m of d of c? That is d, and m of d of d is k into d into under root of 1 minus d. So if you just solve it, you will get two values of d equals to 0 or d equals to k square by 1 plus k square, which is very evident that there are 2 points of intersection for each load line. So d equal to 0 we not consider, we'll take the other point. That is, let's assume that d is equals to d equivalent. Not equivalent, d equal. So d equal is k square by 1 plus k square, where k is r by 12f switching. So at this duty ratio, the buck converter will have the same gain even if it operates at CCM or DCM, it will have the same gain. We have to make sure that d is equals to this k square by 1 plus k square, where k is r by 12f switching. You also observe one more thing, that the discontinuous conduction mode of operation for a buck converter will give more gain where d is between 0 to d equivalent for any load condition or any inductance. So here there are multiple graphs of m of d of d. Those graphs are for different inductances L1, L2, L3, where L3 is greater than L2 is greater than L1. Why? Because k is inversely proportional to n. So m of d is greater than m of d of c for d lies between 0 to d equivalent. So DCM gives more gain than CCM in this range, and in the other range it is vice versa. So now we finished with the analysis of discontinuous mode of operation of buck converter. Now we'll see the discontinuous mode of operation of boost converter. So this is the circuit diagram of the boost converter. Now we'll quickly draw the waveforms. So these are the switching pulses. Now in the discontinuous conduction mode, just like the buck converter, the boost converter also will have 3 modes of operation. In CCM we used to have 2 modes of operation, that is when the switch is on and when the switch is off. When the switch is on, diode is reverse bias, and when the switch is off, diode is forward bias. Now in this case, apart from these 2 conditions, we get the third condition in which the switch is also off and the diode is also reverse bias, which means that both the semiconductor switches are turned off. So there will be an additional mode 3. So the circuit diagram for mode 3 I will draw here. Mode 3 is like both of them are open. This is the inductor, this switch is open, and this is open, and this is the load. So in this case, this is VS1 and this is VD. IS1 is 0 and ID equals to 0. In that case, what happens? IC equals to minus ILoad, and this is IL. What is IL? IL is 0 in that case. In that case, if IL is 0, there will be no, so this will be VL plus minus. In this case, if the current through inductor is not, what do you say? If there is no current across the inductor, there will be no change in its voltage, because VL is L DIL by dt, which means that here the inductor voltage is also 0. So in that case, VS1 almost equals to Vin, and in that case VS1 equals to VD plus V0. So VD becomes equals to VS1, that is Vin minus V0. So this is the mode 3 of operation, where IL equals to IS1 equals to ID equals to 0 and IC equals to minus ILoad. So this is the case. So now we'll draw the first we'll draw the waveforms of the inductor. So first we'll draw VL. Now the here this time, first we'll write this time is D into T switching, and this time is 1 minus D into T switching. So if you draw VL, the switch is on, the inductor voltage is equals to V in. This is equals to V in. And with the switch is off, the voltage across the inductor is V in minus V naught, but V naught is greater than V in, so it becomes negative. So it is negative. This is V in, this is V in minus V naught. And then there is a third state where the voltage across inductor is 0. So this third state is between these states. Again it is V in minus V naught, and again 0. So this is the point where which we'll get the discontinuity. It's in the off time only. If we draw IL will be, when the voltage across inductor is positive, the current through it rises. When it is negative, the current will fall. So current will fall. And when there is no voltage across inductor, what happens is the waveform gets clipped off. Yes, when the voltage across it is 0, the waveform gets clipped off. So actually here I have started it from some positive value, but this whole waveform will be shifted downwards, because the part of this waveform here will be clipped off. So I'll draw both the waveforms, CCM as well as DCM. Oh. So like this. What happens? First I'll draw for CCM. So this is rising and this is falling. This is IL for CCM. Now IL for DCM, if I draw, it will be like this. This part of waveform will be clipped off. It will be like this. So this will be the ultimate waveform of IL. This triangle. So what happens is, now this range, this is what? Delta IL of D, that is discontinuity, and this whole is delta IL of C, from here to here. This is delta IL of C, or delta IL, continuous conduction mode. So this is IL. Yeah, so as I said earlier, the reason of discontinuity in a buck converter can be two things. First is insufficient inductance, L as an L critical, or second thing is the minimum load or very less load. But in the boost converter, the inductance can't be minimum inductance. We have to have some minimum inductance across the boost converter. We cannot operate a boost converter in no load condition, because we already know that the capacitor voltage, the capacitor will violate its amp second balance and it will go on building its voltage, which may damage the converter. So we put some minimum load across the boost converter, and we have also calculated in the previous lectures what is the value of this minimum load. So minimum load of inductance, the idea behind calculating the minimum load of inductance is very similar to finding the critical inductance of inductor. So it means that the point at which the waveform of inductor current where IL minimum touches 0, that is only the point of critical mode of operation, and that is only the minimum load. So it means that here in this case, load is not the mostly the reason for discontinuity. The reason is the insufficient inductance. Okay, the reason is the insufficient inductance. And in the waveform of IL, if inductance changes, then the slope of the waveform also changes. So in this case, we will modify the waveform of the inductor current according to this understanding. So we'll redraw the waveform of the inductor. First is plus V. This is the inductor voltage. Then I'll directly draw the waveform of the inductor current in DCM. It rises in this region, it falls, and then this is the clipped off part. This is the inductor current. So here we have drawn the inductor current in IL of CCM and IL of DCM. So the slopes are changed and the waveform is pushed down. So this is how the inductor current will look like. So see here that the start point of the inductor current, that is this point, is not equals to start of the inductor voltage waveform. It is shifted. Why? Because the waveform is pushed down. Okay. So in that case, this becomes the delta IL of D, and this is the delta IL of C, or delta IL. This and this is delta IL. So now we have drawn the inductor waveforms. Now we'll draw the switch waveforms. For volt second bias, we need only the voltage waveform of the inductor. First we'll draw the switch voltage. First, when the switch is on, the voltage is 0. When the switch is off, and when the diode is on, the switch is off, the diode is on, and thus the voltage across the switch is equals to minus V0. No, the voltage across the switch is plus V0. So it is plus V0. This is 0, this is V0. And when the switch and diode both are off, that is in mode 3, Vs1 is almost equals to Vin, and Vin is less than V0. So it is like this. Again 0, V0, Vin. So this is Vs1. Now we'll draw Is1. When the switch is on, Is1 equals to IL. So I'll draw in green color only. So it is like this. Is1 equals to IL. When the switch is off, the current through it ideally should be 0. Similarly, for third case, it is 0. The waveform is like this. Only a triangle. This is Is1. So the inductor is done, the switch is done, then comes the diode. when the switch is on, the voltage across diode becomes VD becomes minus V0. When the diode is off, voltage across it becomes 0. This is 0, this is minus V0. And for the third case, VD is V in minus V0. So V0 is greater than V, so it is negative, but slightly more than this. So it is this. Here it is V in minus V0. Similarly, it is V0, 0 and V in minus V0. This waveform belongs to VD. We'll again use green color for the waveform of ID. When switch is on, diode is off, so the current is 0. When the switch is off, the diode is on. In that case, ID equals to IL. So it is like this. This is ID. Now the capacitor current, we'll assume that I load is constant. So ID is IC plus I load. So ID has some average value plus ripple. So ripple should go to the capacitor and the average value should go to I load because I load is constant. So we'll just push the waveform of ID to downwards. So the waveform of IC becomes this. With 0 average value. This is IC and ICC dV by dt. So voltage is integral of IC. So if we draw V0 or VC, it will be first is integration of a negative term. So it will be a minus of a ramp function. So it will be a falling function like this. Falling function of like this, then falling polynomial of, because it is ramp signal, so integration of ramp is a polynomial function, a quadratic function with falling edge like this. So it will be like this. Then again constant falling ramp negative, then again a polynomial, so like this. So this will be the nature of, this will be ripple nature of V0. This will be delta V0. Delta V0. So this time, this new time here is D dash into T switching, which we want to find. So using amp second balance, what we'll write? Amp second balance for this. So here this will be A1, this area will be A1, this area will be A2, and this area will be A3. So A3 basically has no area here like this. So what will do, volt into second, so VL sigma VL into T, that is sigma VLI into TI equals to 0 for 3 cases. So for I equals to 1 to 3, that is VL1 T1 equals plus VL2 T2 plus VL3 T3 equals to 0. Now what is T1 T2 T3? This is T1, this is T2, and this is equals to T3, where T1 is D into T switching, T3 is what? D dash into T switching, and T2 is what? This whole is 1 minus D into T switching. So T2 is this minus this. T2 is 1 minus D into T switching minus T3, or minus D dash of T switching, which becomes 1 minus D dash of T switching. So we substitute here, what is VL1? VL1 is V in, and VL2 is V in minus V naught. So V in into D into T switching plus VL2, that is V in minus V naught, into T2, that is 1 minus D dash into T switching plus VL3. What is VL3? VL3 is 0. So no term will be here, equals to 0. So T switching will be cancelled. The remaining terms are V in D is equals to V in minus V naught into, or it will be reversed, V naught minus V in into 1 minus D dash. So if you brought all V in terms of LHS, it will be D plus 1 minus D dash equals to V naught into 1 minus D dash. D by D will be cancelled. So V naught is V in into 1 minus D dash by 1 minus D dash, which means that M of D for discontinuous conduction mode, which is V naught by V in, is 1 minus D dash by 1 minus D dash. This is the expression. So we'll quickly verify. When the switch is on, voltage across inductor is V in. So VL1 is V in. The switch is off, voltage across the inductor is V in minus V naught. And for the third case, it is 0. And T1 is D into T switching, T2 is T off minus T3, where T3 D dash T switching. So 1 minus D dash into T switching equals to 0. So now we have to replace the D dash in terms of known parameters. So now first we'll replace D dash in terms of known parameters. So we'll use for replacing D dash, what we'll do, we'll let VL is L DIL of D by dt. So this we can break into 3 terms. That is for T1, VL equals to V in, for T equals to T1, VL is V in minus V naught, for T equals to T2, and VL is 0 for T equals to T3. So VL equals to 0 will not use, and T equals to T1. What is T1? T1 is D into T switching, and VL is V in. We want to replace D dash in terms of known parameters. So if we use T equals to T1, we'll get in terms of D, we'll not get in terms of D dash. So we will not be able to replace it. So we'll not take this, we'll take only T equals to T through. So VL equals to VL2, VL1, VL3. So VL2, that is V in minus V naught becomes equals to L in discontinuous conduction mode, because L is different, into delta IL by delta T. What is delta T? This is the delta T. Delta T is T2. What is T2? T2 is 1 minus T minus D dash of T switching, or we'll write F switching. Now if we just solve it, 1 minus D dash will be LD into delta IL of D into F switching by V in minus V naught. So what will be D dash? D dash will be 1 minus D minus LD into delta IL of D into F switching by, if we write V naught minus V in, it will be positive, then this becomes positive. This is the D dash. This is the very first equation. So let's write it as very primitive equation, first equation, and let's write this as second equation. So 1 minus D dash is we have derived. Yeah, so D dash this. If we substitute, or let's write this as 2, because it's easy to substitute. So using 2 and 1, what we get is, in 1 we'll substitute the terms of 1 minus D dash as this, and we'll put it in equation number 1. So therefore V naught by V in, which is 1 minus D dash divided by what? This term, equation 2. So it will be what? 1 minus D dash. What is 1 minus D dash? From equation 2, that is LD delta L of D F switching divided by V in minus V naught. This we have written. So if we write 1 minus D dash equals to what? V naught delta L of D into LD into F switching divided by V in into V in minus V naught, like this. 1 minus D dash is V naught into LD delta LD F switching by V in into V in minus V naught. Or what we can write? We can write is a D dash minus 1 by replacing this. So we'll write V naught minus V in, V naught minus V in, and we can erase this. This is equal to D dash minus 1. So D dash is what? 1 plus V naught LD delta L of D F switching by V in into V naught minus V in. This is some expression. So now we got the expression of this D dash. Now D dash is here as well as here. Let's equate these two D dash so that D dash will be eliminated. Then we'll get the expression of V naught versus V in terms of delta L of D. So equating this d dash with this d dash, what we'll get is, first is 1 minus d plus ld delta L of d f switching by v naught minus v in is equals to 1 plus v naught into ld delta IL of d f switching by v in into v naught minus v in. This we have equated, so this gets cancelled, and the final expression of this will be what? It should be this. So this term we'll send it on the RHS and we'll rearrange it. So D will be this. So now we have eliminated D dash. That's a good thing. But now the headache is delta L of D. This we have to replace. How to replace delta L of D? If we again try to replace, again it will come in terms of D dash. So it will be a cyclic process. So now instead of eliminating D, what we'll do is we'll use the proportionality theorem. The proportionality theorem is that, so that assume this is, so this is the inductor current waveform, correct? This whole is delta IL. So this waveform is clipped off for the discontinuous conduction mode. In that case, this becomes delta L of D. Now generally, what is delta L? VL is L dL by dt. So this is VL into L by delta T. Because VL is L, sorry, this becomes L comes in denominator. VL is L VL is L delta L by delta T. So therefore delta L will be VL delta T by L. So generally in the boost converter, the discontinuity here is due to, let's assume that it is due to the inductance. So the product, so delta IL is inversely proportional to this, or we can say that the product of L into delta IL is constant. This you assume. Whatever is the case. That is for T equals to T on, that is D into T switching. So D into T switching is constant for both this thing, at continuous conduction mode as well as discontinuous conduction mode. So this relation we can write L into delta L is constant. So L continuous into delta L continuous is what? LD into or instead of writing this, we'll write this in terms of criticality. So the first case we'll assume it as the critical conduction mode. So here it is, L critic into delta L is LD into delta L of D. So what you will get? Now delta L of D is what? L critic delta IL by LD. LD is the inductance at which the converter is operating in the DCM mode. So L critical for boost converter we have written already. L critical is what? This one. So this is the L critical. So what will be delta L of D? It is delta L into D into 1 minus D whole square R divided by 2 LD into F switching. Yeah, so this is the thing. Now we'll replace this delta LD in this equation. Let's say this is what equation number 3 and this is equation number 4. So using 3 and 4, what we get is we'll substitute delta L of D in this expression of we'll substitute delta L of D from equation number 4 in equation number 3. So equation 3 will rearrange. We'll write D into V naught minus V in equals to LD F switching into 1 minus V naught by V in into delta L of D. Delta L of D is delta L into D into 1 minus D whole square into R by 2 LD F switching. These two will be cancelled. So now it will be in terms of delta L. So D into V naught minus V in is equals to 1 minus V naught by V in into D into 1 minus D whole square R by 2 into delta L. So we can write what delta L as VL1 into delta T1 by L LD. What is BL1? When T is T1. T1 is D into T switching. It is what? It is V in. So V in into D T switching, that is D by F switching into LD. So this we substitute it here. So therefore what will get D into V naught minus V in is equals to 1 minus V naught by V in into D into 1 minus D whole square R by 2 into F delta L, that is V in D by F switching LD. We have to rearrange this equation so that it will be so we'll let minus V naught minus V in by V in into D square V in R into 1 minus D whole square by 2 LD F switching. So this will be cancelled with this. Yeah, so the remaining terms are this. We'll send the denominator towards the LHS. So it will be D V in into 2 LDF switching equals to minus D square into V in R 1 minus D whole square. So here Vn will be cancelled. If we simplify it, it will be, if we take V0 minus Vn common, if you want to find a generic approach for finding the DC transfer function for any DC-DC converter operating in the DCM or the discontinuous conduction mode for any converter, say buck boost or buck boost converter, so instead of following the previous approach, what we'll do is we'll have a simplified approach. So here what we'll do is by neglecting the losses, so the same was the assumption while we were deriving the DC transfer function for any converter in the continuous conduction mode or CCM. Same assumption we will consider here in DCM as well, that is input power equals to output power without any losses. The same assumption we'll put here, that P in equals to P naught where this thing is, where P naught is V square by R, that is output power. So we have to find the input power. Okay, we have to find the input power. Now what is the input power? P in is V in into average value of input current. Now in a buck converter, the input current is not equals to the inductor current. Input current is equals to the switch current. And as per waveform, so if we see the waveform, so let us say first we'll write a generic approach. Generic approach of DC gain in DCM. So first thing is P in equals to P naught. P naught is V square V naught square by R. And what is V in? P in? P in is V in into I in. So it is P in is V in into average value of I in. V in is constant, so V in is V in, and I in is a waveform, so we have to find the average value. We are equating the average power. So in all the converters, what we have to do is we have to replace this in function of, as a function of average inductor current. Okay, so for doing that we'll refer to this waveform. So this is the waveform. So this is the inductor current, this triangle one in DCM mode. Now as you know, the reason of discontinuity, as I said, there can be two reasons. First thing is insufficient inductance, and second thing is the load, insufficient load. Now what happens is this inductor current is having some band. This is delta IL here, which you can see, this is delta IL. Till here only, and then it goes like this. So this is the band. So it can go in discontinuous mode, that is below the zero axis. If it goes below zero axis, means it is DCM mode. So there are two reasons for this inductor current to go in the negative direction, and as we have a diode, the inductor current cannot conduct, so the waveform gets clipped off. So here you can see this waveform is clipped off. This waveform of inductor current gets clipped off. So that's why it is discontinuous conduction mode. And now the new inductor current becomes like this. So it becomes 0 in this case. This is the waveform of IL. So there are two ways in which this current can go beyond the or below the zero axis. First reason is this band, this delta N. So the reasons for DCM, first is L less than L critical. So how does L affect the discontinuous? It widens the band. What happens is, as L increases, delta IL decreases, or I can say vice versa. I am saying that L is less than L critical, so I am reducing the inductor. So what happens? The band delta L increases. So as the band increases, the waveform can go in the negative direction, which can get clipped off. So that's why that can result in discontinuity. Second result is R is less than R minimum. R minimum is the R at which the waveform is critically conducted. Similarly, L critical is the inductance at which the waveform is critically conducting, means that L minimum is 0. So how does R affect the inductor current waveform? Is its average value. Average value means the DC shift. This is the average value. See this is the average value from here to here, capital IL or capital IL. So there are two ways in which this triangular varying waveform can be in discontinuous conduction mode. First is the band in which it varies, that is the delta L. So what changes delta L is the inductance. If we reduce the inductance below L critical, then the band increases in such a way that it goes in the negative direction, which results in discontinuity. Second is its average value. So don't change the band is fixed, but the waveform is moving up and down. So if the load is less, R is less means the load is more. So if R is more, the average value is less. Vice versa, because resistance and the load current has the inverse relation. So if the load is not sufficient, the waveform is pushed down, and it is pushed down in such a way that it gets clipped off. So that's why that is another reason for discontinuity. So we'll assume that now our converter has different R and L with respect to the same converter operating in CCM. Because if our converter has the same value of L and R as in CCM, then it will not operate in DCM, it will operate in CCM only, because the waveform is not going below the zero axis, means it is not clipping off. So we'll assume that we don't know the exact reason of discontinuity. We'll assume that both L and R are that is both the inductance and the value of load at the converter are different from that in the CCM, but rest other things are same, that is the value of V in, V0, switching frequency, rest everything is same. So we'll assume that L in this case is LD and R in this case is RD. So in DCM, L equals to LD and R equals to RD, that is discontinuous mode. So that's why the waveform is like this. So let's find the average value of IL. Here the average value of IL, that is the average value of this triangle. Which triangle? This above triangle, not the clipped off one, the above triangle. So in this waveform you can see x1 and x2, and here you can see this angle theta1, this theta1, here this is theta2, this is theta2. This part is delta IL of D, that is in the discontinuous conduction mode, and this whole is delta IL from here till here. So we can use tan theta is opposite by adjacent. So tan theta1 is what? Delta ILD by x1, which is also equals to delta IL by T1, because this time is T1. This time is T1. T1 is equals to T on. And this is T2 and this is T3. T2 plus T3 is what? T off. And T off is 1 minus D into T switching. T on is D into T switching, which is D into T switching. And T off is 1 minus capital D into T switching. Here T3 is D dash into T switching, and T2 is what? T off minus T3. That is 1 minus D dash into T switching. These are the times. So by using this, what we can get is delta. We can so what we want to find is the average value of IL. So average value of IL is what? 1 by T switching, integral 0 to T switching, IL of T dt. Then what is this? This is the area under IL versus time graph. So if we transfer TSW to numerator, it will be F switching into area. We are finding the area. What is the area of this waveform in a switching period? It is half into base into height. What is base? Base is x1 plus x2 and height is delta L of D. So we have to find x1 and x2. So by using the tan this is equals to tan theta 1 and this equals to tan theta 2. So this thing tan theta 1 is delta L d by x1, which is also equal to delta L by t1. Similarly, delta L of d by x2 is delta L by t of, because the angle is same, using the symmetric property of triangles, equilateral triangle. So what we are doing is we are finding x1 and x2 in terms of the known parameter, that is delta IL d, delta IL t of, and t1. So we'll get x1 and x2. If we add x1 and x2, which is the total x, is what? Delta L d by delta L into f switching. So in that case, what is the area? Area is half into base into height. Base is x, height is delta L d, which is this. So delta L d and delta L d is there, so it will be delta L d square. So average value is, therefore average value is area into switching frequency. So this switching frequency gets cancelled because it is multiplied. So it will be delta L d square by 2 IL. So I'll write average value of IL is delta IL of d whole square by 2 2 into delta IL. Now this delta IL was the value of the ripple when the converter was operating in the CCM conduction mode. That is when the load was R and when the inductance was L, not for LD and RD. So we can write VL is L delta IL by delta T, or we can write delta IL as VL into delta T by L. Delta L as VL into delta T by L. Now it is this thing. Now, as also I have said that we don't have to write in terms of d dash, because d dash we don't know. We have to write in terms of d. So that's why we will write, because we know that t on will be d into t switching for all the converters, buck boost or buck boost, irrespective of anything. And VL on, so here we can write VL on into t on divided by L. T on is d into t switching or d by f switching. So it is VL on into d by f switching into L. L in continuous conduction mode. D is same for both. We are assuming that duty ratio is same for both the converter, means same converter operating in both CCM and DCM. The only thing is that the inductance is less than L critical, which may be the one of the reason for going in discontinuous conduction mode, or when R is less than R minimum. Rest everything is same. We'll assume that the converter in both the mode operate on the same duty ratio, that is D, capital D, not D dash. So that is same. So delta L is VL on into D by F switching L. So if we replace in terms of delta IL, average value of IL, which is delta IL of D whole square by 2 into delta L. Well, delta L is VL on into D by F switching into L. Similarly, we can replace delta LD. So similarly, what is delta L of D? VL on into D by F switching into LD, because the inductance is changed. So by substituting, therefore average value of IL is equals to F switching L by 2 VL on into D into VL on square D square by F switching square into LD square. Now F switching and L, not L will not get cancelled. F switching, this will get cancelled. VL on, this get cancelled. D and this gets cancelled. So in the numerator, what is the remaining thing? VL on into D into VL on into D divided by 2 F switching into what? L by LD square. This is the term which we get, average value of IL. Once we'll recheck it, F switching VL on and D will get cancelled, and we'll get VL on D by switching, VL on D by 2 F switching to L, VL on D by 2 F switching into L by LD square, because L and LD are both are different, so it won't get cancelled. Yeah, so this is average value of IL. So if you substitute average value of IL in this expression, P in, so we have to do converter wise. First, for buck converter, because we know average value of IN, we have to substitute IL as a function of IL. That changes from converter to converter. So for buck converter, average value of IL is what? Sorry, not IL. IN is what? So this is the waveform of buck converter. This is IL, and this is IS1 or IN, input current, because input current equals to the switch current. Now here you can see that out of the waveform of IL, only the waveform which appears in the D into T switching time is means IL equals to IN when T equals to T on. Rest it is 0, which means that IN is T on times of IL, that is D into IL. D means capital D, so IN is capital D into IL. IN is capital D into IL. So therefore, now we'll write the power expression. P in is what? V in into, so therefore V in into average value of IN, which is D into average value of IL, equals to V naught. V naught is, sorry, P naught. P naught is V square by R. R is RD. So here we will write RD. Now we'll substitute V in into D into VL on into D into L by 2 F switching LD whole square is equals to V naught square by RD. Now we don't know what is VL on. VL on means what is the value of VL when the switch is on. Now for a buck converter, which is here, when switch is on, what is the value of VL, voltage across inductor, is V in minus V naught. So VL on is V in minus V naught, that we have to substitute. V in minus V naught, which is positive because V naught is less than V in. So therefore it will be V in T square L into V in minus V naught by 2F switching LD whole square equals to V naught square by RD. Then we have to simplify and solve this expression. It will be D square RDL into V in minus V naught equals to V naught square into 2F switching into LD whole square. So what we'll do is we'll divide. First we'll see if everything is correct. D square L into RD into V in minus V naught equals to 2F switching LD square into V naught square. Yeah, we'll divide on both the sides with V in square. So what happens? This and this gets cancelled. So it will be D square RDL into what? V in by V in is 1 minus V naught by V in equals to V naught by V in whole square into 2F switching LD square. So let V naught by V in is M of D for D. So it's a quadratic. So therefore, or let's assume that it is X. So therefore X square into 2F switching LD whole square plus D square RD L into X minus D square R D into L equals to 0. x square into 2f switching LD square. It was minus sign that side, so here it will be plus d square RDL into x minus d square RD into L equals to 0. So we'll find x using the quadratic rule. This is A, this is B, and this is C. So x is minus b plus minus under root of b square minus 4ac by 2a. So x, that is v naught by v in, which is also equals to m of d for discontinuous mode, is minus b, that is minus d square rdl minus b plus minus under root of b square, that is d to the power 4 rd square l square minus 4 into a, that is 2 f switching ld square 4a into c, into minus minus becomes plus d square rdl divided by what? Divided by 2a. So 2 into 2, 4 f switching ld whole square. So here what we'll do, we'll make it rd square and we'll divide it by rd, and we'll take d to the power 4 rd square l square common in this term and this one, and we'll bring out it out of the square root sign. So it will be minus d square. Okay, yeah. Also here we'll let d to the power 4 and denominator will put d square. So we are taking common d to the power 4 rd square into l square. So here will become l square and here it will be l. So minus d square rdl plus minus d square rd into l under root of 1 plus, it will be what, 4 into 2, 8 f switching 8 f switching ld square rest there is nothing in the numerator, divided by d square rdl whole divided by 4 f switching ld whole square. So this is the expression of the gain for a buck converter in DCM mode in terms of the known system parameters and also in terms of the parameters for CCM, that is L and LD and RD. So similarly, second case for boost converter. For boost converter, average value of input current is average value of inductor current, because inductor is placed at the input side. So therefore, V in into average value of IL. What was the generic expression for average value of IL? That is VL on. This will just copy paste. V in into IL is equals to V naught square by RD. And what is VL on? When the switch is on for a boost converter, VL equals to, I think it is V in. Yes. When the switch is on, VL equals to V in. So it is V in. So this is equals to V in. So simply it will be V in square dl by 2 f switching ld whole square equals to v naught square by rd. So v naught by v in is square root of what? dl rd by 2 f switching ld square. I think this is the expression for the boost converter. rd into dl by 2 f switching ld square. This is equals to m of d for d. What is m of d for continuous conduction mode? That is v naught by v in is 1 by 1 minus d. Similarly for buck converter, m of d for C continuous conduction mode was d only. So this is how we should find the DC gain for CCM. But as we don't know what is the reason of CCM, so that's why we have to do this thing. So in this case, as I said that for any converter, there are two reasons of discontinuity: insufficient load or insufficient inductance. Now for a boost converter, we already know that boost converter cannot operate at no load. So in this expression, in the expression of buck converter, if you are saying that the converter operates at no load, then at no load RD becomes infinite. So what you can do is, in this expression, you can take common of all RD terms and you can make it this thing. So that's why but a boost converter cannot operate in no load because it violates the amp second balance principle. So we are already, in any case, we have to put some minimum load at the output of the boost converter or any boost derived converter, which we have already derived in the previous lectures. So assuming that we already have sufficient load on the boost converter and the expression for R minimum and the expression of L critical were almost same. That is, same principle was used for deriving both the expression. That is, L is equals to L critical, which means that the inductor current waveform, the IL minimum is 0, which almost touches the 0 axis, means it does not go in discontinuous conduction mode. So that's why the only reason for a boost converter to operate in DCM is only due to the insufficient inductance and not the load, minimum load. So in this expression of this thing, we'll say that RD is always greater than R minimum, and R minimum was the R which we already derived in the previous lectures. So we can assume that RD equals to R, which is for CCM. So so this was for boost converter. For we quickly derive for buck boost. For buck boost converter is like this: input side, then I think we have a switch, we have an inductor placed here, then we have a diode, then we have a capacitor and a load. So when the switch is on, VL on is equals to V in, and what is this is I in. Average value of I in is what? So this is the inductor current I in, and this is the diode current. So IL equals to I in when T is on, and I in equals to ID when T is off. So which means that IN is D times IL. Oh sorry, here I should write IL D times IL. So therefore V in, that is P in, that is V in into IL in, that is D into IL, is equals to V naught square by RD. This is RD, V naught, and this is LD, assuming that it operates in DCM now. So the expression of IL will write So V in into D into, we'll paste this expression, and VL on, what was VL on? VL on is V in, so V in. Okay, so V in into this is equals to V naught square by R D. So D square L by 2 F switching into LD whole square. If you bring RD here, it will be V naught by V in. If you bring in the square root side, it will be this. So M of D for D, which we can also write as D by LD under root of L RD by 2 F switching. This is for DCM, for buck boost converter. And what is M of T for continuous conduction mode? It is minus D by 1 minus T. Or what we can write is, we will write in terms of mod. Here we will write mod of this is D by 1 minus T. So similarly, in boost converter, what we said that we cannot operate it in no load condition. So there is no question of the converter operating at minimum load so that the inductor current becomes discontinuous. So it means that R in this expression RD is equals to R, which is for CCM, which is greater than R minimum. And R minimum is derived considering its critical conduction mode, which means that it never goes in DCM. So even for a buck boost converter, the only reason for operating in DCM is due to the insufficient inductor. So this is how we have derived the DC gain for buck boost and buck boost converter. Now if you see, some people, what they do is, the waveform of IL which they consider for deriving the expression, what they do is they consider it starting from 0 and falling. Then this is discontinuous, and again like this, which is not correct. So what we have to do is, like this they do, where what they do is, this for them this is T on, this is T off, and this is what we have considered as D dash T off, sorry, D dash into T switching. They directly start the waveform from 0. But the thing is, so actually what should happen is, because the whole waveform, what happens is, either the band can change or the average value can change, which may bring this waveform to the discontinuity. That's why the waveform not necessarily to start from 0, it can start from any random point. So what we are doing is, we are establishing a relation between this waveform with respect to the continuous current waveform of inductor. That's why in the expression, in our expressions, we have got in terms of L and LD also. So this we have to do. This is the right approach. So if we do not use this approach, what they do is, as per their analysis, in this expression there will be only one inductor where L equals to LD, and by equating it, there will be L will come here in the denominator, and then they consider it as the L discontinuous. But the thing is, we have to establish a relation of the waveform in DCM with the CCM, because CCM quantities are known to us, and the only thing or the only term that comes in this waveform of CCM is only L, because LD is for DCM, RD is for DCM, rest F switching and capital D are same for DCM as well as CCM, because the T off is same. We are assuming that the converter operates with the same duty ratio, okay, that is capital D. But the reason for discontinuity are two. That is the insufficient inductor. So if the inductor is insufficient, if L is less than L critical, the waveform band or the delta will increase. If it increases, it may go in the negative direction and the waveform will be clipped off. So it is DCM. Second reason is the insufficient load. So if the average value of inductor current is not sufficient, the waveform will be pushed down. So if L is fixed and only load changes, then the waveform is moved up and down, where the band of delta L is fixed. So if the load is minimal, the waveform is pushed down. So it may cross 0, it may go below 0. So that's why this portion is clipped off, and it is in DCM. So while comparing the DC transfer function of a converter, of the same converter operating in DCM and CCM, we have to assume something to be constant, and those things should not contribute to the change of mode, that is from DCM to CCM. That is, we'll assume that Vin is same, V0 is same. We'll assume that switching frequency is same. In fact, switching frequency also affects the DCM and CCM, but the ultimate thing that affects is the circuit parameter, that is L, and load, that is R. Because if switching frequency changes, the frequency at which, because in the expression of L critical is a function of switching frequency. If switching frequency changes, L critical changes. So L may go less than L critical, which may result in discontinuity. So this is indirect reason of discontinuity, but the ultimate reason is the inductor and the load, by assuming that switching frequency is constant. So that's why we have to establish a relationship between the inductor current waveform in DCM and CCM mode. That's why here L and LD both are separate, and we have got the three expressions. So if we simplify, so the waveform of MD of D for boost and buck boost are simplified. For buck, we'll simplify it. What is M of D of discontinuous mode is this. We'll take D square RD by L common. D square RDL by 4 F switching LD square. It will be -1 plus minus square root of this term. I hope I have written it correctly. So my D square RD L by 4F switching LD square common -1 plus minus under root of 1 plus 8. Yeah, it is correct. So this is the expression. For boost, M of D was under root DLRD, or we'll just copy paste. Okay, under root of DLRD by 2 F switching DLRD by 2 switching LD square. And for buck boost, D by LD square root of LRD by 2F switching. For this case, M of D for CCM is 1 by 1 minus T. For this case, M of D for C is minus D by 1 minus T. And here M of D for C is D. So if you plot first for buck converter, Here is D and here is M of D. First we'll plot for CCM. So 0 and then it moves in a straight line. This is 0 for a buck connector, 0. This is 1. So this is 0.5, 0.75, 0.25. This is also 0.25, 0.5, 0.75 and 1. This is a linear relationship where this is M of D for continuous conduction mode. Now for discontinuous conduction mode, here it has a square expression and it is multiplied to this term here. So we'll assume that as D lies from 0 to 1, so it's a fraction. Okay, it's a fraction. So we are doing square of fraction, so which will be further less. Okay, so it will be further less. So, and here in this case, d square is in the denominator. So this expression will be a very big expression, 8f switching LD square by d square RDL. This will be a very big expression. Okay, so the thing is, this expression, we have to find this expression with respect to this expression, because here it is LD square by L. So assuming that LD and LD and L will be in millihenries or microhenries, both will be in the same range. So ultimately the L expression will be in the numerator. Let's say it is kilohertz, and this is milli. So powers, this power will get cancelled with this power, so remaining is only 8. So 8 by d square into RDL. So this expression will be greater than this expression. This is 1, this is 2. So 2 is greater than 1. But the thing is, to make it positive, 2 has to be greater than 1. So we'll discard the negative sign here. And the thing is, here this expression number 2. So if 2 is greater than 1, we'll assume that we'll neglect 1 and we'll assume only 2. So 2 is multiplied with this. And in this 2 there are two expressions, 1 plus this. So we'll neglect this and we'll consider only this. So what happens is, again it is square root of this expression. So this expression is multiplied with this expression. So this will slightly affect the gain of this expression. But this is a dominating term here, d square. So it's almost similar to y is x square, because this is y and this is x. So y is x square, almost equal to y is x square. So like this we can plot it, y is x square, whose gains are slightly changed. Like this fashion. Slightly it will change. At d equals to 0, this expression is what? Infinite. So basically this is 0. 0 into something is 0. At d equals to 1, what is the value of this expression? So it is something. Yeah. So this is M of D and this is, sorry, that is M of D of C and this is M of D of D, discontinuous conduction mode. So it may or may not intersect this one, but yeah, so instead of drawing this, let me draw like this. The gain may be very high at d equals to 1. So it intersects somewhere here. So let's call this as Let's call this as D equal, where M of D is equals to M of C. This is D equal. So from 0 to D equal, gain of continuous conduction mode is greater than discontinuous conduction mode, and further it is vice versa. So we can find D equal, where M of D will equate M of D equals to M of C, and we'll find the D. What is the D in that case? So that analysis you can do. That is some complex analysis, but you can simplify and do it. So quickly, if we do for boost converter, so what it will be? For a boost converter, M of D for C is 1 by 1 minus D. So 1 by 1 minus X is like this. It starts from 1, this is 0, 0.5, 0.75, and 0.25. So say that this is 1, this is 1. So at D equals to 0, gain is 1, and gain increases like this. At 1 it reaches infinity, so the curvature is more, it goes more upwards like this. This is M of D for continuous conduction mode. Now if we plot for DCM, it has a term of root square root of D, so y square root of x. So y square root of s looks like this. At D equals to 0, it is 0, and then it goes on like this. This is M of D for D. It's obvious that at D equals to 0 or at very less D, gain for continuous conduction mode is greater than gain for discontinuous conduction mode. And this waveform may or may not intersect. That depends on what is the value of this term, LRD. So, and for a buck boost converter, it is like this. M of D for C is negative, so minus D by 1 minus D. So it starts from 0 and then it falls like this. And M of D for D is almost similar to y equals to mx, so constant gain. So it is first we write this as M of D for C, and this will be M of D for D for a buck boost converter. So it's clearly visible that there is no advantage for operating a buck boost converter in discontinuous conduction mode. So because the thing is, if we just change the position of this switch like this, if we change the polarity of it from positive to negative like this, if we interchange it, then this waveform will move up. So it will be like this. This will be M of D of C mod. So then you will get something interesting. Then you will observe that at less duty ratio, discontinuous conduction gain is more than continuous conduction gain. Then there comes some advantage of operating the converter in the DCM mode or discontinuous conduction mode, because in discontinuous conduction mode the advantage is that we'll require less inductance and we'll get more DC gain. So where we want more gain, we can use DCM with less value of inductance needed. So we'll stop the lecture here. And so we have analyzed the discontinuous mode of operation of these DC converters, and we have derived we went with steady state analysis with the waveform, and we tried different approaches for finding the DC gain in DCM, and we have correlated the this inductor current waveform, this inductor current waveform in DCM versus CCM mode by using triangle properties, and we tried to derive it in terms of the known parameters or the CCM parameters, and then thus we derived the DC gains. And then we derived some conclusion that what should be that, so what are the advantages of DCM mode, which converter for which duty ratio or which duty ratio range, which mode of operation gives more gain. So that we saw here by using this analysis. So for boost convert, so basically m of d is a function of d, and it's multiplied with some term. So we'll assume that this term is some k. So we'll say that let k is under root of L Rd by 2 f switching Ld whole square. This is some k. So therefore, in this case, m of d will be what? For a buck converter, so it is difficult to raise. So m of d is what? Root of d into k, because it is k times multiplied here, and here it is dk. So m of d is d into k, and k is directly proportional to what? Inversely proportional to switching frequency. Inversely proportional to switching frequency, inversely proportional to the what? The inductance, and directly proportional to the load. So we can get different waveforms like this, different waveforms of MD like this for different operating conditions. So this is at K1, this is K2, this is K3. Similarly, like this we can get different slopes at some different K1, K2, K3. Similarly for this converter, K1, K2, K3. So if switching frequency increases, K decreases, so this thing falls down. So if switching frequency increases, the waveform moves, as if switching frequency increases and the L increases, the waveform moves down. And if R increases, the waveform moves up. R increases means the load decreases, then it moves up. So this is how we have done the analysis. So we'll stop here. Thank you.